Okay, we're starting a new module, Module 3. The name of this module is just similarity. So one thing that you might want to do is to think, and we discussed this in class, to think about what does it mean for two figures to be similar as opposed to being congruent. Remember, for congruent shapes, we could map the shape directly onto the other shape or figure, and it would coincide exactly. For similar, and you may have learned this in the past, they are the same. Basically, what we've kind of learned is that they're the same shape, but not necessarily the same size. So in this this first lesson, and actually in this whole module, we're going to be learning a more precise definition for similarity based on a new type of transformation called a dilation. So let's go ahead and get started. Find the first page of lesson 1, the classwork, and you'll see these images. And this is an exploratory challenge. So I'll introduce it to you, and then I'll have you pause the video and work on that, and then you can start the video again. All right, and so what this says is that two geometric figures are said to be similar if they have the same shape, but not necessarily the same size. Using the informal definition, are the following pairs of figures similar to one another? And it says explain. So just a brief explanation as to what you're seeing there. So you've got some triangles, some rectangles, looks like pentagons, circles, and then the next page has 4 more pairs. So pairs A through H, go ahead and pause and just say whether you think those are the same shape, but not necessarily the same size for each of those pairs. And then just a brief, really brief description. Okay. Okay, so when we discussed this in class, most people looked at pair A, the 2 triangles there, and thought, yes, they are similar. They're both obtuse triangles, and they look in proportion to one another. So, so we said yes on that one. For the next one, for pair B, most people said no, those are not similar. One looks like a perfect square, and the other one's a much taller rectangle. So they're not in proportion. So for pair C, we thought yes, those are. In fact, not only are they similar, they also look congruent. They look like they're the same size and the same shape. Looks like we could do some transformations and map one directly onto the other. Okay, and then also in pair D, those are both circles. So they are the same shape, obviously different sizes. Okay, continuing on to the next page, the arrows in pair E. We had a little disagreement on this one. A lot of people thought, yes, they look similar. We would have to do some ratio comparisons to know for sure. They look similar, but you could say yes or no on this one and make your case. All right, so pair F, most people thought yes, that looks like a similar smiley face there. And but in pair G, this one looks like it's been munched down or stomped on. So no, those don't look similar. Okay, and then pair H, these 2 curves, most people said no, they don't look like the same shape, because one is very narrow and tall, and the other is is opened out wide. Okay, so those we just did a very informal look at pairs of figures and said whether we thought they were in proportion to one another or not. All right, I've created a little video for you with a Superman image, and you'll find it in the playlist titled Stretching and Shrinking in Proportion or something like that. And you can watch that now if you'd like. It's something you're pretty familiar with. It's how to resize a picture on a diagram. So you can watch that now, or you can go back and watch it later. So a precise definition of similarity or same shape is going to center around this idea of dilation. In class, we talked about the word dilate. A lot of people had been to the eye doctor and had their eyes dilated, which is enlarging the pupil so that the eye doctor can see back into your eye and look for different types of diseases and things like that. So you might think that to dilate means to enlarge, but in fact it can mean both. It can mean both to enlarge proportionally or to shrink proportionally. So a dilation is a transformation, and it's a transformation in the same way that translation, rotation, reflection are transformations, but it's a little bit different in that it's not going to leave things the same size, obviously, because we just said it's going to either magnify or shrink. Okay, and so it's a transformation of the plane. You need to have two things. Like remember for a translation, you needed a vector. For a reflection, you needed a line of reflection. For rotation, you needed a center and the number of degrees, or the how far you're going to rotate it and in what direction. For a dilation, we need a center of dilation. We're going to call it O. We'll call it O usually. We can call it whatever we want. It's a point, okay? And we need a scale factor, okay? And we'll call the scale factor R. And so for these, we are going to, we'll name our dilation, so we could name it D. So there's going to be a couple things that happen. The center never moves, so the dilation of the center is just the center. It will never move, no matter what our scale factor is. We're shrinking and enlarging or magnifying, but the center stays the same. But every point, the dilation of a point P, if for a point P that's not the center, the dilation of P is is defined so that the length from O to P is equal to the scale factor. We'll make that P prime. The length of OP prime is the scale factor R times the length of OP. Okay, and a picture is going to help us with this. So if I have a center of dilation O, there's my point O, and I've got a point out here P that's not O. Here's my point P right there. I can draw a line through O and P like so. There's some distance here, OP, okay? And if I want to magnify that, say I want to double that distance, I would have a point out here called P prime, and the distance from O to P prime is going to be, if my scale factor is 2, like it looks like here, the distance from O to P prime is going to be twice the distance from O to P. So if I look here, O to P is a certain distance, and O to P prime is going to be multiplied by something. Okay, so let's talk about scale factor for a minute. Okay, so if I have a figure like this rectangle here that's very kind of a little bit sloppily drawn, but you can see that it is roughly, whoops, I've got to get a different tool here. It is roughly 3 by 6. I meant for it to be exactly 3 by 6. So it is 3 by 6. If I wanted to enlarge that by a scale factor of 2, so if, I'll just use R, because we're going to use R for scale factor. So if R equals 2, that means I'm going to be multiplying all the sides of this rectangle by 2. So I would end up with a rectangle that was twice as wide. So 1, 2, 3. Looks like about 12. 1, 2, 3. Okay, that's 12. 12 wide, and then it would be 6 in this direction. Okay. So I'd end up with a rectangle that is 6 by 12. And 6 is 2 times 3, and 12 is equal to 2 times 6. Okay, so all the dimensions increase by 2. Okay, so that's a scale factor, R equals 2. You've done this before. So what if I took my original triangle again and I said R is equal to 1/2? So what would that mean to change this original rectangle by a factor of 1/2? Well, I would have 1/2 of the length here and 1/2 of the width, or whatever you want to call it, the height. And I would end up with a much smaller rectangle. So what would that look like? Oh, let's not use 1/2. It'll be easier to draw if we use 1/3. So we'll use 1/3. Okay, so if R equals 1/3, same thing, right? I can put down, so 1/3 of 3 is just 1, and 1/3 of 2 is 2. I'm having trouble drawing this one. So it'd be that by that. Okay, so that would be shrinking by a scale factor of R equals 1/3. This ended up being an enlargement with R equals 2. Okay, and what about if R equaled, well, let's have you answer that. What would R be, what value would R be if I wanted a congruent rectangle to this one up here? What if I want to get a congruent rectangle, what scale factor would I use? So you might be thinking, well, what if you use R equals 1? Because then I would just be multiplying the sides by 1. I would come up with a congruent rectangle. And so I don't need to draw it. But if scale factor R equals 1, then it would be this one right here. So let's go back and talk about that in terms of dilations, because we're going to use, this is kind of a review of how you've used scale factor in the past. And so let's look at it, what it means in terms of a dilation. Okay, so thinking about dilation again, we have our center of dilation O, which is right here, and we have a point. We can dilate any point on the plane as long as it's not O, because remember the dilation of the center is always going to be the center. It's not going to move. It's the thing that stays in the same place. So we can draw this ray from O through P and going on forever, basically. And if we look at, so obviously P is going to be on that ray. So if we look at this distance, and I'm using these absolute value bars to mean the distance between O and P. Okay, and if I look at the distance between O and P prime, it's going to be the scale factor R multiplied by this distance OP, okay? So this is the basic diagram for dilation right here. So let's talk about what happens when a point gets dilated. So let's take a couple cases. We looked at scale factors equal to 1. If the scale factor is equal to 1, nothing moves. Okay, so point P would stay in the same place because P wouldn't move because I'm only multiplying by 1. So P prime would be in the same exact location if R equals 1. The figure, so if R equals 1, then our original figure has no change. Nothing moves. Okay, so no change. So we're going to look at two other cases. What if R is greater than 1? So that would be like the scale factor we just talked about that was 2. If R is greater than 1, then points are pushed, we could say, pushed away from the center. And that's this situation here. This would be, this diagram up here, keep doing that, would be us. So here's our point P, here's the dilation of P. It's pushed further away from the center if R is greater than 1. So it'd be a number like 2 or 3. This looks like about 3. The distance is about triple to the image that it was from the original point. Okay, but another situation would be R less than 1, but still greater than 0. So we want it to be positive, and that would be a number like 1/2 or 1/3, right? A fraction. And it would, what this would do is all the points are pulled towards the center. Okay, so I could draw you a picture of that so that you could see what that is. But think about it, if I've got this distance here and I multiply it by a fraction, then my image is going to end up somewhere in this area. And so my my dilation is going to be pulled toward the center for R less than 1 for fractions, and it's going to be pushed away from the center for R greater than 1. Okay, so let's look at a picture of that, and then I want to show it to you on GeoGebra. You can do these dilations on GeoGebra, and that's pretty cool. So let's first look at what that picture would look like if R is less than 1. Okay, so I had a little bit of room here to put that, and you'll see it in your lesson. So here was my original point. There's my original distance, OP. If I multiply by a fraction, here is OP prime. It's smaller. It's closer to the center. So there's less distance between there. So I had to have multiplied by a fraction or a number less than 1 when I did this R right here. When I did this R times OP, that would be this down here. R times OP would be closer to the center. Okay, and you're going to do some exercises like that. But I want to show it to you on GeoGebra now. Okay, in order to show it to you on GeoGebra, I had to put it in a separate video. So go find that now in your playlist and watch it, and then come back and finish watching this video. Okay, so let's look at what happens to a segment. So say I've got this center of dilation. I've got a point P, and say I've got this ray going through those 2 points, And what if this distance is 3 centimeters? If I have a scale factor of 4, r equals 4, what would be the length of OP prime? So OP prime would have to equal the scale factor 4 times the length of OP. Okay, so I know that the length of OP is 3 centimeters. So this would be 4 times 3 centimeters, just substituting for the length of OP. So OP prime would be 12 centimeters. Okay, so let's go back. What if my scale factor was less? What if my scale factor was 1/2 in this same situation? Well, the same thing is true. The length of between O and the image of P, or P prime, OP prime is going to be the scale factor times OP. Same thing is true. This time our scale factor is 1/2. The length of OP is still the same at 3 centimeters. So our distance from O to P prime, remember we're using these bars to mean distance, it would be 1/2 times 3 centimeters, which would be 1.5 centimeters. So OP prime would be 1.5 centimeters. Okay, so this is basically the definition of dilation right here, this box, saying that the distance from the center O to P prime, this distance from O to P prime is what this means, is equal to some scale factor times the distance from the center to my point. Okay, so we're going to be doing some problems like this. Okay, now find exercise 1, which is on this page where we had the pairs of figures right at the bottom. Exercise 1 gives you a length of OP, so that would be the distance from the center, this one right here, the distance from the center O out to some point P is 5 inches. And we're given a scale factor and asked to find the length of the segment between the center and the image of P, or P prime. So go see if you can do those on your own, and then come back, do 1A and 1B, and then come back and check your answers here. Okay, so for 1A, I'll write it up here. So we know that by the definition of dilation, we know that the distance from O to the image of some point P is equal to the scale factor times the distance from O to the original point, or the center here, O, to the point P. Okay, so this is the main part of the definition of dilation. So for this 1A, we can see that the distance from O to the image of P is going to equal our scale factor. So we're looking here, we're looking at this equation right here. We're looking at this equation here. So now I'm going to put in 4 for the scale factor and 5 inches for the distance from O to P, because that's what we're given. Would be 4 times 5 inches. So this would be 20 inches. So that would be the distance from the center out to the point P prime, the image. Okay, and in this case, so you can see this is going to be pushed away from the center because the scale factor is greater than 1. Okay, but the length of OP prime when the scale factor is 1/2. So that'd be 1/2 times 5 inches is going to be 2.5 inches. Okay, so in that case, P is 5 inches away. So scale factor of 1/2 is pulling toward the center of rotation. The center of dilation, sorry. And going to put the image at 2.5 inches from our center here. So OP prime is going to be 2.5 inches, so it's pulled toward the center. Okay, I'm going to read you the directions for exercises 2 through 6, and then we'll do the first couple together, and then I'll have you do the others on your own. Okay, so we've got this diagram, and we're going to use it for all these remaining exercises. So there's a dilation from center O, right here. There's a dilation from center O, and the dilation of P is equal to P prime. And the dilation of Q is Q prime. So in the diagram below, the distance from O to P is 3 centimeters, and the distance from O to Q is 4 centimeters as shown. So here's our dilation, and the rays have been drawn for us, because remember that the image of a dilated point is going to be on a ray coming out from the center of dilation through the point itself, the original point. Okay, so if the scale factor is 3, what is the length of segment OP prime? So that would be this length here. And use the definition of dilation to show that your answer to exercise 2 is correct. Okay, so go ahead and do number 2, and then we'll check it, and then I'll show you what you should write for number 3 to use the definition of dilation. Okay. So for 2, if the scale factor is 3, then the length of segment OP prime is going to be 9 centimeters. So you could just say the length of OP prime is 9 centimeters. And using the definition, we can just say that the length of OP prime is equal to the scale factor R times the length of OP. Okay, so the length of OP prime is equal to the scale factor 3 times the length, which is 3 centimeters, and so that is 9 centimeters. So again, we're using this definition here for finding the dilated points. Okay, so go ahead and do exercise 4 and 5. You're doing the same exact thing for point Q, and then we'll come back and talk about exercise 6 together. Okay, so check your work on exercises 4 and 5. The length of segment OQ prime is 12 centimeters, and using the definition, we can see that this length of OQ prime is the scale factor times the length of OQ. So that would be 3 times 4 centimeters, or 12 centimeters. Okay, that's pretty straightforward. Okay, so what if we didn't know the scale factor, but we knew the two lengths? So what if we knew that the length of OP was 3 and the length of OP prime was 9? How could we use that information to determine the scale factor? Okay, so once again, we know that the length of OP prime is equal to the scale factor times the length of OP. And if we solve for R in this equation, notice if we divide both sides by OP, we're going to get that the scale factor is just the dilated segment length, OP prime, divided by the original segment length. Okay, so that's how we define scale factor. It's how many times bigger is so it's how many times bigger is the dilated than the original down here. And so in this case, we would see that the scale factor is 9 centimeters divided by the original length, which was 3 centimeters. So this scale factor is just 3. And notice it doesn't have, scale factor does not have units. It's a multiplier only, okay? So centimeters cancels out, and we end up with just this unitless number that we multiply by. And that's important with scale factor, that it doesn't have units. Okay, and I want you to notice something too, that what if our image was shrinking? Going back to this kind of formula for R, we solved for R. If say we got smaller, what if our original, our dilated segment was 1 centimeter, and originally it was 3 centimeters? So that would be a situation where the image is being pulled to the center. So we've got this 1 centimeter dilated. So what would our scale factor be in that case? Well, it would be a fraction, be 1/3. It would be a multiplier like that. So that doesn't go with this problem, but just so you can see that to get these fractional scale factors, it requires that the distance to the image be smaller, so that we have a smaller number in the numerator than in the denominator, giving us a number less than 1. Okay, so what we're going to do now is just look at the lesson summary, and then you can get going on the problem set. Okay, so in your notes, and your problem set, if you turn to that, your problem set for this, pass the exit ticket, you'll see the lesson summary. So we've gone over all of this, and this gives the detailed definition of a dilation. So a dilation is a transformation of the plane with center O, scale factor R, and R is greater than 0, remember. And this transformation is a rule that assigns to each point in the plane a dilation point, we can call it P prime, so that two things happen. If we dilate the center, so the dilation of the center O is just O. So the center does not move. We talked about that. If there's a point P that's not the center, then the dilation of P, and we're going to call it P prime, is a point on the ray OP, so that OP prime is equal to R. The distance from O to P prime is equal to the scale factor times the distance from O to P. Okay, so those are the things we talked about. So we use this mainly when we talk about the definition of dilation. This is the heart of it, that we multiply by the scale factor to find the location of the dilation of point P. All right, so that kind of sums up lesson 1, and you can work on the exit ticket and the problem set, and be sure to check your work so that you're getting the vocabulary correct and kind of just using the correct logic and terminology. All right, good luck with that.